Hi, everyone. Thanks a lot for attending our session. It's a late evening, so I really appreciate you coming down and attending the session. So I am Ankush Desai, and along with me is Vikas Behra, and we are both super excited to be here talking to you about how you can gain confidence in your system's correctness and resilience using formal methods. Okay? And I know that as soon as many of you heard formal methods, you might be wondering, okay, so this talk is going to have a lot of math in it, it's going to be super heavy, and may not be generally applicable for the kind of systems that you're kind of trying to build. And my response to that is, it's none of the above. Okay? There is going to be no math in this talk. I'm going to provide you a very gentle introduction to formal methods. And in particular, if you're trying to build a distributed application where reasoning about correctness and resiliency of your system is hard, then the techniques that we're going to talk about in this session is applicable to your system and problem. Okay? So what I'm going to do is I'm going to provide you introduction to formal methods, and then we're going to talk about a framework called P, which we have been using inside AWS for reasoning about correctness of systems. And then Vikas is going to come in and tell you more about how, as AWS customers, you can use these techniques and gain confidence in your own workloads. Okay? So let's get started. Let's get started with the problem itself. Why are we here? We are here because we all agree that programming distributed system applications is challenging. It's like putting together a complex piece of puzzle where each piece of puzzle needs to fit in perfectly so that the system that you're trying to build is reliable, is fault tolerant, is correct, is resilient, and so on, right? When you're trying to build a distributed system, you would definitely want your distributed application to satisfy certain desired specifications or requirements, right? Scalability, high throughput, availability, n nines of availability, multiple region, or correctness properties like consistency. And you would want your distributed application to satisfy these specifications in the presence of all the non-determinism that exists in a distributed system. Failures, node failure, network partitioning, message loss, message getting delayed, AZs going down, and so on, right? And when you want your distributed system to satisfy all these desired specifications in the presence of all the non-determinism that exists in your application or distributed system, the system that you end up with building is never going to be a monolithic system. It got to be a compositional system where there are multiple services, multiple components, multiple protocols interacting with each other to together ensure that your application satisfies those desired specifications, right? Now, when you have all these complexity, reasoning about correctness and resiliency is hard, right? Which is why we have all these guardrails in our development process. We have these guardrails so that we can find design-level logical correctness bugs as early as possible in our development process. And we all know that finding a logical or correctness bug in our design late in the development process has a high cost and effort associated with it, which is why we would like to catch them as early as possible in our development process, right? So the question is, what more can we do? What additional guardrail can we add in our development process so that we can solve this issue, right? And that is what this talk is about. That is what this session is about. We strongly believe that formal methods could be that additional guardrail that you can add in your development process that can help you in gaining confidence in your system's design when you are building a complex distributed application, okay? So what we are going to do in this session is first I'm going to talk to you and describe what is formal methods. In particular, what does it mean to think and reason about systems abstractly and above coding? Then I'm going to introduce P, which is the framework which you can use for applying formal methods to distributed systems and applications. How AWS is using it for reasoning about their systems and including it in their development process. Then Vikas is going to come in and tell you about, as AWS customers, how can you leverage P and gain confidence in your own workloads? And finally, how can you get started with P, right? But one of the key takeaways that I would like you to have out of this session is that the process of formal methods has a lot of benefit. In other words, when you're trying to build a distributed system, which is complex, Going through the process of formal methods has a lot of benefits because it helps you in finding and eliminating bugs early on, gain confidence in your system, and in the long run, boosts developers' velocity in delivering robust services. Okay? So hopefully, that's the key takeaway that I will convince you of by the end of this session. Okay? That's the key takeaway. So formal methods. Let's do a quick show of hand to see how many of you have used formal methods in the past or in your team are using some form of formal methods. Okay, great. I see a couple of hands, but that's maybe because formal methods mean different things to different people, right? It could mean a pen and paper proof for someone who is trying to come up with a protocol or a distributed system for the very first time, right? Or it could mean a fully mechanized mathematical proof of the system using a program verifier or a theorem prover, where you get a full proof of correctness. Or it could mean something more automated like model checking, TLA plus, P, and so on. Or in fact, it could mean as simple as testing your system using techniques like property-based testing or lightweight formal methods, right? And formal methods could be considered as any of these techniques. But one thing that is very common across all these tools and techniques is the part about writing formal specifications of your system and checking that your system satisfies those specifications. That's the common part across all these tools and techniques that can be categorized into formal methods. So a simple definition that I normally like to give for formal methods is a formal method is any process that involves writing specifications and checking that your system's behavior satisfies those formal specifications. Okay? And I mean, in this session, we're going to talk, and I'll show you what do I mean by writing specification and how to check them. But the key part, again, that stands out and I have highlighted is the process. When you are trying to build a complicated system, which is hard to reason about, going through the process of formal methods and writing specification and checking is the part that helps you in gaining confidence in your system's design, okay? And I'm not the first one to talk about this, right? Scientists, researchers in our community have been talking about this since ages. The part about the importance of thinking abstractly, precisely, writing down what you're thinking, and so on. So we are not the first one to talk about this, right? But what do we really mean by thinking abstractly and formally? Let's say you're trying to build a distributed system for the very first time, a complex system. And you're not going to start implementing the system right away, right? What is the first step? The first step is to take a step back and think about what is the system that I'm trying to build? What are the components in my system? How do these components interact with each other? What is the assumption that a component makes about the other component? And in particular, and most importantly, what is that customer-facing correctness specification that I want my system to always satisfy? Irrespective of failures, irrespective of message interleavings, what is that specification that my system should never violate? Okay? That's the first thing. Once you have a clear understanding of that aspect of your system, that's when you move on to implementation. But thinking is not enough, right? What is important is to think at the right level of abstraction. What I mean by that is when you're thinking about your system design, it's important that you only think about those parts of your system design that are important from the point of view of correctness and ignore things that are there for the reason of performance or implementation level detail and so on, right? For example, one very simple experiment that I conduct when I'm trying to understand a distributed system design is I'm looking at a pseudocode, and then I ask questions like, hey, what would happen if I comment out a certain piece of code? Would it break my customer-facing specification? Or is it just there from the point of view of correct, like performance and implementation level detail? Like gaining that level of understanding in your protocol design is important before you move on to implementation. And obviously, okay, thinking is not enough. What would be super cool is while I'm thinking, if I could write down precisely what I'm thinking and check that what my design is, it would satisfy the desired specifications, right? That's the eventual goal. And obviously, when you're trying to build a complicated system, designs are not static, right? So each time you make changes in your design, it would be great if you could go through this process, iterate through this thing. Each time you make a change, each time you're launching a new feature, you take a step back, think about the changes, make sure they're correct, and check them to be correct, So what do we need? What we need is we need a framework that allows you to go through these iterations, go through these steps. And that's where we have been using P. Okay? So P is an open source programming framework available on GitHub. It's a programming framework for reasoning about distributed system. P provides you a high-level state machine-based programming language where developers and system builders can express their system design as communicating state machines, which is how normally they would think about as distributed system design, right? So you can capture your system design as state machines that are communicating with each other by sending messages. And once you have expressed your system design in P as state machines, what P provides you, it provides you a backend checker that explores all possible behaviors of your system and checks that for those behaviors, the system design satisfies the desired specifications, right? And once you have done that, you gain confidence in your system's design. But then obviously, system design, validating that is not enough, right? Because implementation is what gets shipped, not the design. So P provides you a way in which you can connect your design level specification to implementation and make sure that your implementation also aligns with the design level specification. Okay? So those are the three parts. And as you could see, P is a framework that then allows you to achieve what we discussed in the previous slide. Go through those iterations of design and gain confidence in your design's correctness before you move on to implementation. Okay? So P is being used inside AWS, like teams across compute, storage, databases have been using P to reason about the correctness of distributed protocols that drive these services. Okay? For example, P was first used for reasoning about the correctness of Amazon S3 strong consistency protocol when S3 was going from being an eventually consistent system to being a strongly consistent system. And the service team were planning to make several changes in their protocol stack to make sure that the system satisfies strong consistency property. And that's when the S3 team used P to create formal models of their protocol stack, wrote down detailed interactions between how the components interact with each other in P as state machines, wrote down the correctness specification that the system must satisfy, in this particular case, consistency, and then use the P checker to systematically explore the design space of the protocol stack and make sure that the system design satisfies the required specification in the presence of failures and message interleavings and so on. Okay? And as you could see, that since the P checker is doing systematic exploration of the design space, the probability of the P checker finding a bug in your system is much higher than what it would be if you used the traditional testing approaches, right? And hence the service team, S3 team, was able to eliminate several bugs in their design early on in the development process itself and gain confidence in their protocol stack that guarantees strong consistency, okay? So you might be wondering what is happening underneath the P checker, right? Like the way to think about what the P checker really does is you could think of it as an engine that does systematic exploration of your state space. Let's say your system is in a particular state, and in this case, when I say a system, it's the model, the formal model of your system modeled in P. And there are multiple actions that can happen simultaneously, maybe failure or messages being sent and so on. And what the P checker really does is it explores all possible combination of messages and failures in your system. And for each of those reachable state, it asserts that your system satisfies the desired correctness specification. Okay? And I know that many of you who have built complicated systems might be wondering at this point, okay, for a complicated system like this, my state space is just huge. The combination of failures and messages that can happen in the system is just huge, and this kind of systematic testing may or may not scale. And that's where the magic of automated reasoning and math comes in, is the backend checker, which uses all these techniques to scale analysis of complicated distributed system, and that's where the mathematical part comes in, and that's the backend checker for P. But the important part that I want to convey was that, and it might be very obvious to you as well, is that the reason why P checker is able to find bugs faster and low probability bugs is because it is reasoning about your system at a high level of abstraction. So because of which, the probability of it uncovering a bug is much, much higher than you trying to uncover that bug using traditional testing approaches like stress testing, implementation, integration testing, and so on. Right? That's the key part to understand here. So what we've been doing at AWS is we've been integrating formal methods in our development process. So the traditional development process would be design, code, test, and then deploy. What we do is we do p-validation before we go on to implementing our system. Gain confidence in our design before moving on to implementation, and iterate on the design itself until we have kind of like narrowed down a design where we are confident that it satisfies the desired specification under different faults and failures and so on. Okay? So I know at this point we know about what formal methods is, we know about what P is and how AWS is using it. Now is a good time to look at an example for P because I know that seeing is believing, right? So that you start believing what I'm saying. So for that, what we're going to do is we're going to use a very simple example of a two-phase commit protocol. Okay? It's a very well-known protocol for guaranteeing atomicity of transaction in distributed systems, where, for example, when a client sends a write transaction to coordinator, you want the protocol needs to make sure that this transaction is either committed by all the participants in the system or it's not committed by any of the participants. So it's an all or nothing protocol. Okay? And the way it works in two phases. In the first phase, when a coordinator gets a write transaction request, it asks each of the participants in the system, hey, can you commit this transaction? And based on the local state of the participant would say, hey, I can commit the transaction or I reject the transaction. And in the second phase, the coordinator, based on the responses that it received from each of the participants, would either commit the transaction or abort it and then send the corresponding response back to the client. Okay, that's the very simple two-phase commit protocol, and it works in these two phases. So let's say you are the one who came up with the two-phase commit protocol for the very first time. Okay? How would you go about reasoning about the correctness of this protocol? The first thing is, like I said, take a step back, think about the components in your system, and think about how you would reason about them, right? So in this particular case, there are two components, coordinator and participant. And I want to think about the coordinator. How would you think about the coordinator? The way you would think about the coordinator is as a state machine. You would say, okay, the coordinator starts in a wait for transaction state. On receiving a transaction, it sends prepare request to all the participants, waits for prepare responses, and based on the response that it receives, it sends a response back to the client, right? So you could, the key thing I wanted to communicate here was that you would think about your components as state machines that are receiving messages and evolving, okay? And similarly, you would model the participant. That's how you would create a high-level design for your distributed application or system, okay? What about specification? Specifications are part of the are things that your system must always satisfy. So for example, global invariants. These are properties that your system must always satisfy. In the two-phase commit case, the invariant that we want our system to always satisfy is atomicity, right? So if a transaction is committed, then it must be accepted by all the participants in the system, or and it must have been accepted, and only then it must be committed. That's the global invariant. So how do you think about that global invariant? So one way to think about it in terms of execution is, let's say there is an execution in the system, and you saw a write transaction come in, and you saw that your system responded to the write transaction as being committed. Then the invariant that your system must satisfy is that it must always be the case that in the past, all the participants in the system must have agreed to commit the same transaction. And similarly, if the transaction was aborted, then there must be at least one participant in the system which said that I cannot accept the transaction, so that you know that your system is not arbitrarily rejecting transactions, right? So that's how you think about global invariants. And this is one of the global invariant that you would want your two-phase commit protocol to always satisfy for atomicity, okay? So now you know how to think about your system's design as state machines, how to think about global invariants. So what are the parts that are involved in modeling this kind of system in P? So the first would be, like I said, create participant and coordinator state machines in P, write down a client machine in this particular case that bombards events onto your system under which you want to check its correctness. Okay, you can think of it as environment system or model that bombards inputs and failures onto your system under which you want to check the correctness of your system. And finally, you write the specification that observes the state of the system and asserts them to be correct. Okay? So these are the three parts that are involved when you are reasoning about your system using P. So now is a good time to look at the P program. Okay? So like I said, there are three parts. The P source folder contains the state machines that you want that are involved in the system, spec folder that contains the invariant, and the test folder that contains the environment that is bombarding inputs and events onto your system. Okay? Those are the three main parts in a P program for whenever you're trying to reason about your system. In P, state machines communicate with each other by sending events. So for example, line number 27 here declares a write transaction request with a payload of type T write transaction request. And P is just like any other programming language. It allows you to write user-defined types and complicated types so that you can capture complicated protocol logic in P. Okay? And you basically would declare all the events that are being used to communicate between different components in your system, and that acts as an interface between your components. So in this particular case, the events that are being used to communicate between the coordinator and the participant. Okay? So the events that are used to between state machines. Now let's look at a state machine, the coordinator state machine. Each state machine in P has a set of local variables. These are local to the state machine and used to store the state of the state machine. So in this particular case, for example, participant to store the set of participants, the current transaction that is being processed, the set of transactions that I have seen in the past, and so on. Okay? Each state machine has a start state. In this particular case, the init state, and an entry function that gets executed when you enter the state. And these entry functions could be any piece of arbitrary imperative program, like P supports for loops, while loops, if-then-else statements, function calls, and so on. So you can actually write complicated protocol logic in P. Okay? So in this particular case, broadcast events to all the participants and jump to the wait for transaction state. Okay? And when you enter the wait for transaction state, you would basically have two handlers. And based on the events that you receive, you execute the corresponding event handler. Okay? So the key thing that I wanted to highlight here was that if you look at it, P is just like any other programming language, but it provides you syntactic sugar of state machines to capture your design of the system as state machines, which communicate with each other by sending messages. Okay? So it provides you this high-level abstraction of state machines so that you can build designs of your system at that level of abstraction. So that's about the coordinator, and you would write a participant state machine and so on. Let's look at how you write specifications in P. Specifications in P are also like any other state machine. There is no math. You don't write specifications as mathematical formulas, but you write them as special type of state machines that observe events that are happening when the system is executing. So, and maintain some local state of your system so that you can assert some global invariant. So in this particular case, you maintain a map that stores what are the responses that were being sent by the participant. So, and based on the responses, you update that map. Okay? And as you're observing the system as it's executing. And then when you receive a write transaction response event in your system, and you see that, based on the response that you saw, let's say success, you would assert the thing that you should have seen all the participants send success, or if I saw an error, then at least one of them must have said that I cannot accept the transaction. Okay? So the key thing, again, I wanted to highlight here was that specifications are not mathematical formulas, but they are just programs. You write programs that observe the state of the system and assert the global invariant that you want to assert on your system. Okay? So that's why it's easy to use for developers to think about specifications and everything as programs. Okay? How do I test my application in P? It's just like any other programming language. You write test cases, You run them, and the P checker underneath checks all possible interleavings of the state machines and messages that are being modeled in your system, and says if there is a bug found or not. So let's say in this particular case, instead of waiting for n number of participants, I wait for n minus 1 number of participants and run the checker again. It would lead to a violation of the atomicity guarantee, right? So it finds, when you run the checker, it again explores all possible interleaving and finds an execution for you where a sequence of messages would lead to the violation of that message, and you can look at the error trace that gives you the sequence of messages being exchanged between coordinator and participant and go through those error traces. Okay, so it's as like testing and running the P checker is as simple as testing any other program that you in any other programming language. Okay, so what we also provide is a framework called PZ for making use of P easy peasy. So where basically the error traces that are being provided by the checker you can use a trace visualizer to debug the error traces of the distributed system. And we also provide a way in which you can visualize the state machines that are being used for modeling your system design and add them in your documentation and so on. Okay? So at this point, now you know what a P programming language is, what does it mean to model your system in P and write specifications, check them using the P checker. And the obvious question that remains to be answered is, what about the implementation? Okay, I gain correctness of confidence in my design. How do I gain confidence in my system's implementation? So the way to think about that is, hey, I would like to make sure that my implementation satisfies the same design level specification that I checked on my system's design. Okay? How do I check that? The key insight here is that your system's implementation produces service logs. So which captures the behavior of your implementation when you are testing it and when you are running it in production. So the way we do that, now solve this problem, is we check that your service logs satisfy the desired design level P specifications. Okay? So we have a service called pobserve, which allows you to assert these design level P specifications on your service logs, which could be from multiple nodes in a distributed system and so on, and assert the same specification. These logs could be generated from testing infrastructure, it could be generated from production, and so on. And so you can validate the same design level specification on your implementation and gain confidence that my system is correct. Okay? So at this point, now that you have the overview, I would like to invite Vikas, and he is going to give you an overview of how well you can use P.
Thank you, Ankush. As a solution architect, I develop mission-critical workloads for financial services customers. I often encounter the same set of questions from different customers I work with. First, the customers would like me to validate that the mission-critical workload I'm developing for them will work correctly. Second, the customers would like me to validate that the architectural choices we are making, such as using queues versus streams, will deliver the system goals correctly. Third, the customers would like me to employ chaos engineering to validate that the workload can elegantly recover from transient failures in various components of the system. Fourth, customers would like me to validate that the workload is resilient enough to recover from various disaster scenarios. I reached out to Ankush to see if P modeling can help me achieve all these goals at design time. How powerful that can be. It'll be a huge shift left to be able to do all these activities right during design time. I have no background in formal methods. I'm a regular full-stack engineer. I'm going to share with you my experience working with P to achieve all these goals. One of the mission-critical workload I come across very often is the transaction processing system. whether you're processing payment transactions or stock trade transactions. So first, I created a generic architecture of a transaction processing system with 5 components. The receiver component receives the transaction from the inbound transport. Then the preprocessor component does some form of pre-processing, such as validation, enrichment, etc. Then the processor component performs the core business logic, such as payment processing or trade processing. And then the post-processor component does some form of post-processing, such as enrichment, auditing, etc. And finally, the center component sends the transaction to the outbound transport. Each component in the system is a microservice running on a container with its own database. And all these components communicate with each other through queues. And now we're going to discuss how I created P model for this transaction processing system so that we gain confidence in its correctness and resiliency. One of the central concepts in formal methods is the concept of invariance. Invariants are what you expect to hold true at all times for your system. So for this transaction processing system, the key invariant is that all records published by source are delivered to each of the 5 components and finally to the destination in order. Essentially, it means 2 things. Do not drop a record and deliver them in order. In P model, you describe a system as collaborating state machines. So when you create P model for this transaction processing system, we will design state machines for queues, containers, databases, record source, and record destinations. And all these state machines will collaborate with each other by passing each other events with records as payloads. Now let us design a state machine for a queue. As it is a state machine, let us assume a queue has 2 states, a healthy state and a failed state. In a healthy state, a queue allows a sender to pass a send record event with a record as payload. And the queue, upon successfully processing the record, passes a send record completed event back to the sender with the success status set as true. The queue also allows a receiver to pass a receive record event registering its interest. And once the queue receives a record from a sender, it passes the receive record response event to the receiver, including that record as the payload and setting the success status as true. It tries to simulate the behavior of a queue as faithfully as possible. It also demonstrates how the 3 state machines shown in the diagram collaborate with each other by passing each other events with records as payload. In a failed state, a queue behaves slightly differently. When a sender passes a send record event, queue passes a send record completed event back to the sender with the success status set to false. Similarly, when a receiver sends a receive record event to the queue sends a receive record response event back to the receiver with the success status set as false. This is similar to your experience working with a queue using JMS. When you try to send a message to a queue or try to receive a message from a queue using JMS, the JMS may throw an exception if the queue is not available for any reason. Now let us bring the 2 states of a queue together with straight transitions between them. A queue in a healthy state transitions to a failed state when it receives a fail event. And a queue in a failed state transitions to a healthy state when it receives a recovery event. Now let us see the full state machine for a queue. It has 2 states, a healthy state and a failed state, and they transition to each other in response to a fail and recovery event. It also shows you all the events the queue supports in a healthy state and all the events the queue supports in a failed state. The only difference between the two is that in a healthy state, a queue supports a fail event, and in a failed state, it supports a recover event. Similar to queue, we created state machines for containers, databases, record source, and record destination. Now, let us see the whole transaction processing system come alive as collaborating state machines with events flowing through them. As you see in the diagram, the transaction processing system comprises of 18 state machines, 1 record source, 6 queues, 5 containers, 5 databases, and 1 record destination. And as you saw, the state machines interact with each other by passing each other events with the record as payload. That is how the records get processed through the transaction processing system. Now let us take a look at some key characteristics of these collaborating state machines. 1, each state machine is independent. 2, each state machine is running in parallel at a different speed. 3, each event is asynchronous. So the asynchronous nature of these state machines gives rise to some interesting failure scenarios or defects that would be hard to find using other traditional methods. Now the big question, how do you validate the invariance of the system? P allows you to define a spec that monitors the flow of events. And it uses that visibility into flow of events to validate the invariance of the system. So first, the spec signs up to monitor specific events of interest. It may not monitor all events, specific events of interest. Second, events are delivered to the spec as they're delivered to the target. Third, the spec analyzes the events and validates that the invariants are met. Once you create P model for your transaction processing system, you can create test cases using P to simulate various test scenarios and validate the behavior of the system during those test scenarios. P allows you to specify how many iterations you want to run and how many records to publish in each iteration. You may choose to run 10,000 iterations with 1,000 records in each iteration. With such large number of records being processed by these asynchronous state machines running in parallel at different speeds, you're likely to find bugs that you won't find otherwise. I implemented 3 test cases, and each of these test cases are executed in an automated fashion. The first test case I executed was to simulate standard processing when all the state machines are healthy. When I executed the test case, it published a set of records from the record source, and it validated that all records in the set are delivered to all the components in order. If at any point of time, any of the invariants are not met, it identified a defect that I had to investigate and fix. And this is how I verified that the transaction processing system I designed works as expected when all the state machines are healthy. Second, I implemented a test case to simulate chaos engineering where we randomly fail a number of state machines, a number of components in this architecture, and then recover them, and then monitor the behavior of the systems during the recovery process. So when I execute this test case, it publishes a set of records and confirms that all the records are processed successfully by all the healthy state machines. So that's the good state. Then it failed a random set of components and published a second set of records. It randomly failed 2, 3, 4, or 5 state machines here. Then it recovered the failed components and published a third set of records. It confirmed that all records in the 3 sets are processed successfully. If at any point of time the invariant wasn't met, then it pointed to a failure scenario where a specific state machine or a set of state machines fail. When I ran this test case thousands of times, it would work fine 990 times. Then it would fail randomly once, highlighting a very specific scenario where a specific set of state machines fail in a specific order to highlight that one specific scenario that I need to go and fix. This allowed me to push chaos engineering to the limit at design time. How powerful that can be for you. The third case I implemented was for failover validation. When I executed this test case, it deployed these transaction processing systems across two regions, a primary region and a secondary region. And it would run them in an active-passive setup. As shown in the diagram, the system is running in active mode in the primary region as all traffics are routed to the primary region and served from the primary region. So the test case published a first set of records and verified that all the records were processed successfully in the primary region. Then the test case failed the application over to the secondary region and ran it in the secondary region. Then it published a second set of records and verified that all of those records were published successfully in the second region. If at any point of time, any of the invariants were not met, then it identified a defect in your failover process that would go and investigate. We learned a lot of things about transaction processing systems as we created P model for them. Here I'm going to share with you some key lessons we learned about building resilient microservices. We learned that microservices are vulnerable to two kinds of failure: internal failure and dependency failure. In case of internal failure, maybe the underlying compute goes down, bringing the container down, brings the microservice down. But you have auto-scaling in place, then another container comes up and picks up where the first container left and continues processing. This is an example of self-healing architecture. The second scenario of dependency failure is far more interesting. So in this architecture, the microservice running in the container is dependent on Q1, Q2, and the database, each of which is a state machine that can fail independently. For a record to be considered successfully processed, the microservice running in the container needs to receive the record from Q1, write the record to the database, and then send the record to Q2, as shown in the 6 steps in the diagram. If any of the dependency fails, then all the 6 steps cannot be processed or executed, and the record processing would fail. And at that point, we had two decisions. We had a decision to make in our microservices. We could either retry or fail fast. We chose to go with fail fast. And we realized that if you implemented fail fast, when you restore the failed dependency back to health, you have to recover your microservice or container explicitly. To summarize, your microservice can recover from internal failures elegantly using a self-healing architecture. But when a dependency fails, then the microservice needs to be recovered explicitly when the dependency is recovered so that you can establish connection with it. I'll share with you another lesson I learned from chaos engineering. We came across this very interesting scenario where the microservice received a record from Q1. It inserted the record into the database. But before it could insert the record into Q2, the microservice went down. Essentially, the record wasn't totally processed. When we restored the container, we realized that certain records were delivered twice. So we had to implement idempotency logic in our microservice to handle those duplicates. So when I did all this chaos engineering in my previous test case, we came across a lot of such failure scenarios that we had to account for in a microservice design. So in the process, you will strengthen your microservice and make it very resilient with each iteration. Let me share with you my key takeaways from using P for customer workloads. One, using P is easy. P looks similar to any other programming languages like Java or Python, so using P doesn't involve a big learning curve. Second is implementing a P model is fast. It took me 2 weeks to implement the P model for the transaction processing system I've shown you. 3, it detects hard-to-find bugs. If I ran 100 simulations, 99 simulations would run fine, then one simulation would fail, highlighting a very hard-to-find defect. We believe P model will be useful for many different stakeholders. As CIO, CTOs, you can promote a culture of design time rigor. You can require your technology leaders not only design the systems, but also demonstrate that the design will work. Second, as enterprise architects, you create a reference architecture for recurring application patterns. You can validate these reference architectures using P before you share them with application teams. Third, as application architects developing mission-critical applications, you like to express the functional invariance from a domain point of view so that your application is comprehensive. Fourth, as engineers, you will have the opportunity to start with the pseudocode for the components that is battle-tested, stress-tested through thousands of iterations. That will accelerate your engineering work. And finally, as a tester, you will have clear description of the invariance of the system, both from a technology point of view and domain point of view. You will also have clear description of all the components, their states, and their behavior. And you can use all this information to design test cases to test your system thoroughly. Now I'd like to invite Ankush back to the stage.
About how you can use P to do chaos engineering at design time, right? I think we are all used to doing chaos engineering at the implementation thing, do game days and so on, but this is something different. This is gaining confidence in your design through chaos engineering kind of concepts even before you move on to implementation. But I would like to share with you a few more lessons that we learned over the past few years using these techniques at AWS, and then how you can get started with these things and add these concepts in your development process as well. So one of the first lessons that we learned was when you start using P, P is acting as a thinking tool. The reason it's acting as a thinking tool is because it is forcing system builders and developers to answer several questions at design time itself. What are these questions? So first, when you're trying to model your system, formally model your system, the question that needs to be answered is, how is my system going to do what it is supposed to do? How do these components interact with each other? How do they coordinate? How do they achieve what they are supposed to achieve? That's the first question. The second question that they will force you to answer at design time is, what is my system supposed to do? What are the specifications that my system must always satisfy? And that is very important to know in the presence of all the faults. What is the specification that my system can never violate? So the what question. And the final one is the when. Because one can never design a distributed application that can tolerate infinite failures and any sort of random input, right? Your system can only satisfy a desired specification under certain kind of inputs and certain type of failures. So when you are reasoning about your system and doing chaos engineering at design time, it also forces you to think about what inputs and what failures can my design tolerate. Okay? So these are the key things. And what we found was that that is what has magic, right? Because P provides you this domain-specific language, so it forces the developer to think about their system in a different way. And when you give system builders and developers this time to think, they are really smart, and they would extrapolate and find gaps in the system design, which is enough to uncover, in our experience, a large portion of the bugs and gaps in design were just uncovered through this design time thinking process. So it has value and it has magic. But obviously, not all bugs can be eliminated through thinking, right? Like that's where the p-checker, the power of p-checker comes in, because it is doing systematic exploration and find those corner case low probability bugs in your system that require very complicated corner case interleaving of messages and failures for that bug to happen, and the p-checker is able to uncover them at design time. And basically, it's able to find critical bugs in your system early on, and which normally in our experience could not be found using traditional testing approaches. Okay? That's the second lesson. But the key lesson here is that the first two lessons lead to the overall boosting of velocity of developers when they're trying to build complicated distributed system, because now you can iterate through your design faster. You can try out riskier optimizations that you would normally not try out because there is not a good way of testing it. But now that you have P, now that you have a strong validation methodology, you can try out these risky optimizations at design time, gain confidence in its correctness, and then move on to implementation. Okay? So that's the key last lesson that we learned when you integrate P in your development process. So to conclude, what we talked about was that there is a lot of benefit and the importance of thinking abstractly and above coding when you're trying to build mission-critical, important workloads or complex distributed applications. And P is a framework that allows you to reason about your system correctness and resiliency. P is easy to use. It's being used inside AWS, and also Vikas talked about how you can leverage P. It's completely open source. But the key thing that I would like to conclude with is that no matter what tool you use, but going through the process of formal methods has a lot of benefit. Okay? And as a call to action, we would like to work with you to integrate P and formal methods in your development process. So please do get in touch. Through any medium, emails, and so on. P is completely open source on GitHub. There is a full documentation with tutorial available and so on. And the models that Vikas talked about are also available online for you to look at. And with that, we would like to conclude and thank you for attending our session. And please complete the session survey. And thanks a lot. Get in touch. Thank you for attending.